In this video, we talk about building models for viscoelastic materials using what I call the DIESE, D-I-E-S-E method of 5 steps, just that abbreviation can help you remember the steps. Our goal in building models of viscoelastic systems is to convert concepts into differential equations, in this case for stress versus strain, although this system of model development can be used for a lot of different types of different systems models in chemical engineering, mechanical engineering, and electrical engineering. The steps are D for diagram the model, I for identify parameters and variables on the diagram, E for equations determined by the diagram, S for simplifying those equations to remove intermediate variables, and E for error check. In step 1, diagram the system, we build these with elastic elements that are diagrammed like a spring, usually with parameter E for Young's modulus, and a viscous element that we diagram as a dash pot. Think of that as like a bicycle pump where there's a cylinder and a plunger that is the fluid has to move around to go past, and so it's viscous. And we use the parameter eta for this. E, of course, is in pascals, and eta is in Pascal seconds. That's the viscosity. So the elasticity and viscosity. So we have these two types of elements. We can also have a muscle or motor element that produces a given amount of stress, which then is also in pascals. So our second step is to identify parameters and variables. Our parameters are things that are defined in the material that don't depend on the stress and strain of the material. That is, they are the properties of these elements. Variables are the stress and strain of the whole material, for which I usually use sigma and epsilon as we have before, or of elements within the model. So that is, these elements that we've defined above have stress and strain just over those elements, and we usually subscript those because that helps us identify these intermediate ones versus the final ones. So again, our variables of interest versus these intermediate variables. And it's notable that we can sometimes skip things at this point of identifying parameters by using the same variable name when the stress and strains are equal. An example of this step, of steps 1 and 2 with the Voigt model, where there is a spring and a dash pot in parallel. So first we diagram this and we show a spring and a dash pot in parallel. And then we indicate that to say this is the end of our model. Then we need to identify the parameters of interest. So this we'll call E Young's modulus, this we'll call eta. That's the viscosity of the dash pot. And next we need to add our variables. So we need to define sigma 1, epsilon 1 in the elastic, and we'll define sigma 2, epsilon 2 in the viscous. That's just reminding us that that's the stress and strain of those elements. And then we'll define sigma as the stress over the whole thing and epsilon as the strain over the overall model. In step 3, we need to write the individual equations that arise from that diagram. We have two types of equations. We have element equations that relate the stress to the strain in each element. For an elastic element, the stress and strain are proportional. For a viscous element, the stress is proportional to the rate of change in the strain. And in a motor element, the stress in that element is simply prescribed, and it could be just prescribed in a time-dependent fashion. In fact, it generally is. If nothing else, it's turning off and on. And that stress then is independent of strain in that element. Our second types of equations are the conservation equations, and these are the mechanical equivalents to Kirchhoff's laws. The first law is that strains in parallel are equal. We can see that one can't move without the other. In contrast, strains and series add together. The way I think of this is that if there's a component of the material that can stretch by itself, and there's a different component that if it stretches, the material will stretch independent of the first one, then it's the sum of those two stretches that cause the entire material to stretch. Now, the second law talks about stresses. If we have stresses in parallel, then they will have to add. And you can think of that as if your stresses is kind of like force. If you're lifting two things at once, you're lifting twice the total amount. In contrast, our stresses in parallel are equal. And this arises from Newton's law if we assume there is no inertia in the system. So these equations tell us where strains are equal and stresses are equal, and then also the situations where they need to add. And so these give us additional equations in addition to the element equations. Now we know we're done once we have enough equations. We need one equation in order to remove each of these intermediate or subscripted variables like these ones here. You don't need to remove subscripted parameters, just variables. And we also need one equation to keep, because after we've removed a bunch of things, we should be left with an equation with stress in terms of strain. In our example from the Voigt model, we first start with the element equations. We have an upper element where it's elastic, and the elastic element says the stress on that element is proportional to the strain on that element, using here the variables, the intermediate variables on that element. Similarly, in the elastic element, we have that the stress is proportional to the rate of change of strain using the parameter and the intermediate variables for that element. Next, we use the conservation equations. We know that the stresses in parallel adds, and so that allows us to relate the stress in each element to the overall, and that the strains in parallel are equal tells us that each of epsilon 1 and epsilon 2, the strains on the two individual elements, are the same as the overall strain on the object. And we can see this intuitively from the fact that all three of these have to be the same length. In step 4, we simplify the equations. What this means is we're combining the equations to eliminate any of these unknown variables that are not of interest, that is, all the subscripted ones, and we keep only the overall stress and strain and its derivatives, as well as, of course, the parameters that describe the element properties. So this is why I've subscripted the intermediate variables, that is, the ones on the individual elements, so it makes it really easy to know which ones to remove. Hints in this process are to pick one equation you'll substitute things into and then use the rest to substitute them. Helpful tricks are to use the most complex equation as this sort of host or parent equation, use an equation with a derivative, use an equation that has at least one of the target variables. The more of those you can do to pick your original equation, the better. There is no right answer. All of them will give you the same answer. Some of them will just get you there with fewer calculations or manipulations. So once you've picked that, if you need a derivative and you only have an equation with the variable, you can always take the derivative of both sides of an equation to get the substitution you need. Try to get your target variables, the sigma and the epsilon, without subscripts into your equation if they're not already there. Don't worry about introducing a new one in there that's subscripted that's not in there. You'll probably have to do that. But try not to reintroduce a subscripted variable that you already removed. And a lot of times this means you should be wary of using the same equation twice unless you're using it to remove the thing showing up multiple times at the beginning. But you don't want to be using it in the reverse order. You don't want to use it to switch something back and forth. You'll go in circles. Example here of the Voigt model where we do this simplify. So we had said we have these equations. So we'll start with the one that's most complex and that has the derivative, although in this case it doesn't have either variable we're looking for. We couldn't do all of those, you rarely can. So we then use equation 3 in order to put in the sigma and the epsilon. We also then use equation 5, this. And so we replace the epsilon 2 with the epsilon here. And then we replaced the sigma 2 with sigma minus sigma 1. And this achieved getting the original ones in. We got rid of all of the epsilon or the subscripted 2s, so we don't want to bring them back in, but we do need to get rid of the subscripted 1. Then here we simply rewrite this equation. Now at this point, we need to get rid of the sigma 1. And we have two choices. We have equation 1 and equation 2. It's an obvious choice because equation 1 is the only one that has it in it. So we use the equation 1 to replace sigma 1 with E epsilon 1. And now the only one we haven't used is equation 4. And note that I'm keeping track of which ones I've used, because I know that I had to use all of them in order to be able to remove all of the independent variables I created. So now I use that to turn epsilon 1 into epsilon 1 into epsilon right here. Again, all I've done here is change the order so that they are in this form. And that's my final equation. So our fifth step is to error check this to make sure we haven't made a mistake. I always do a dimensional analysis to make sure all terms have the same unit. That can catch a lot of algebraic errors. Keep in mind that E and sigma are in pascals, epsilon the strain is unitless, and eta the viscosity is in Pascal times seconds, and taking a time derivative divides that one by seconds. So I also want to make sure that I've used all of the parameters and I haven't left in intermediate variables. That's really just making sure I'm done. And then a last trick is to find the equilibrium equation, that is, set all the derivatives to 0, and you should have an algebraic equation for stress versus strain, and you can ask, does this behavior make sense given the diagram? Viscous elements can hold no stress. It's like having a missing branch. And so if you look at that, you can think about whether this all makes sense. If you can, you will gain intuition as you do this. So doing this in the Voigt model, we obtain this differential equation. We can check each term has pascals because E is pascals, epsilon's unitless, N is pascals per seconds, and strain is unitless. Divided by dt is 1 over seconds, so that's Pascal seconds divided by seconds is pascals, and then pascals. We can make sure we see both parameters are used, and there's no subscripted intermediate variables. So we did in fact finish. And then we can look at the equilibrium behavior. Well, when we set the derivative to 0, this term falls out, and we're left simply with that epsilon times the strain is stress. This looks like Hooke's law for uniaxial stress, which is what we applied here, which says that once it has come to equilibrium, the viscous element's no longer important, and we have Hooke's law. We could have also seen that we had the dash pot and the spring at equilibrium. The dash pot is no longer relevant, and we're left with just the spring, which makes sense with this equation. So finally, a summary of our model building using this DISA method is we diagram the model, we identify parameters, variables, and intermediate variables. We wrote those individual equations, including element equations for the elastic and viscous elements. We can also use equations for known models that we've already derived. If a model is complex but has within it, for example, the Voigt model we've already seen, you could just use that equation within the other one. Then we also have these distance constraints about and the Newton's second law, the stresses, the rules about stresses and strains in parallel and in series. Then we simplify the equations and error check with dimensional analysis and equilibrium responses, as well as making sure we're finished.